Bismillahirrahmanirrahim. This is PMDC online lecture room. I am Iram Naseeb, lecturer in chemistry. The topic of today's lecture is Law of Mass Action. Dear students, in this chapter we will discuss the law of mass action and expression of equilibrium constant. Law of mass action help us to find out the relationship between the concentration of reactants and products at equilibrium in chemical reaction. It means that in this particular topic we are going to discuss the equilibrium reactions in which the rate of reverse reaction is equal to the rate of forward reaction. That is, the reactions are reversible. This law is presented in 1864. This law states that the rate at which substance react is directly proportional to its active masses, and the rate of chemical reaction is directly proportional to the product of active masses of the reacting substances. Now, what is meant by active mass? Active mass means the molar concentration, that is, number of moles per dm cube in a given solution. Let's take the example. In this particular example, you can see A and B reactants react together to form products C and D. The half-headed arrow shows that the reaction is reversible, and the rate of forward reaction is equal to the rate of reverse reaction. In this reaction, A, B represent reactants while C, D represent the product. Now, the equilibrium concentration in mole per dm cube for all the reactants and products are represented in square brackets, as you can see in this example. According to law of mass action, the rate of forward reaction is proportional to the product of molar concentration of A and B. We can mathematically represent this equation as rate of forward reaction is equal to Kf molar concentration A into molar concentration B. Kf is a proportionality constant and called as rate constant for forward reaction. Kf represent forward reaction. Similarly, C and D are the reactants for backward reaction, so the rate of reverse reaction is given by rate of reverse reaction directly proportional to the molar concentration of C and D. By replacing the proportionality constant, Kr is the constant for reverse reaction, where small r represent reverse reaction. If the reaction is at equilibrium, so the rate of forward reaction must be equal to the rate of reverse reaction. So this equation could be written as Kf molar concentration of A into molar concentration of B is equal to Kr molar concentration of C into molar concentration of D. By rearranging the equation, we can get C with molar concentration into B molar concentration divided by molar concentration of A into molar concentration of B. This is equal to Kf by Kr, that is rate of reverse reaction and rate of forward reaction. This whole term is equal to Kc. Kc is the ratio of rate constant. This Kc is also known as equilibrium constant for a given reaction. Now we can define Kc as the ratio of the product of molar concentration of the product to that of the reactants. Now take another example where the number of moles of reactants and products are represented in a given reaction. In this reaction, small a and b represent the number of moles of reactants and small c and d represent the number of moles of product. Now they are called the coefficient of reactants and products, and the reaction could be represented as Kc is equal to molar concentration of C power small c. into molar concentration of D power small d divided by molar concentration of A power small a and molar concentration of B power small b. This is general form of the equilibrium constant, and it can also be defined as the ratio of the product of molar concentration of the product to that of the reactants raised to the power equal to the coefficient of the respective species that occur in a balanced chemical equation. So, the most proper definition after this discussion for a law of mass action is that the rate of any chemical reaction is proportional to the product of active masses of the reactants, with each reactant raised to the power equal to the coefficient of reactants that occur in a balanced chemical reaction at a given temperature. The value of Kc is independent on the initial concentration of reactant and product, but the value of Kc changes only with change in temperature. Because temperature increases the rate of reaction. If we discuss the law of mass action for gaseous equilibrium, so it is more convenient to express the concentration of gases in terms of their partial pressure. So let Pa is the partial pressure of reactant A, Pb is the partial pressure for reactant B, Pc is the partial pressure for product C, and Pd is the partial pressure for product D. So we can write the equilibrium constant for this reaction as Kp is equal to Pc molar concentration power small c more into molar concentration of Pd power small d divided by molar concentration of Pa power small a into molar concentration of Pb power small b, where small a, b, c and d represents the number of moles of reactant and product as mentioned earlier. Now we can also express the concentration in terms of mole fraction. Then the equilibrium constant is represented as Kx and the term P is replaced by X. Rest of the equation will be the same. And in the similar way, we can also express the concentration in terms of number of moles. So in this case, the X is replaced with small n. The rest of the equation will be the same. You can see the representation in this equation. So this was about today's lecture. Hope you understand that. Here's an assignment for you people. Explain law